Hello, everyone. Last official session of the day. Yeah? All right, make some noise. Let's be awake. Good job. Thank you. Appreciate that. Hi, I'm Priyanka, and I'm your track host. I'm Director of Evangelism at GitLab, and also member of the governing board of the Cloud Native Computing Foundation, or the CNCF, the org that brings you KubeCon. So, well, thank you so much for coming and being troopers throughout the day. I hope you've learned a lot of awesome stuff. I definitely did. This track is the machine learning and data track, which for me is super interesting because I'm from the observability world, and so this is new stuff I get to learn, so that's pretty cool. As with all sessions, it's really important for us to learn what you thought of the knowledge that you gained. So please do go to sked.com after and rate the session. I'm on the program committee, and I can't tell you how helpful it is because every year we get hundreds and thousands of submissions at this point, and having some direction from your ratings is really helpful. So with that housekeeping out of the way, I'd like to introduce the last speakers of this in this room. So Derek from Google and Konstantin from Lyft are going to talk about
Richard.
Oh, shoot.
That's fine.
I don't know. Yeah, the last speaker was Derek. Not that that helps in any way. But Richard from Google and Konstantin from Lyft are going to speak about how when you have ML workloads, they often require a lot of compute resources. When that's the case, and you're using all kinds of abstraction layers, there's Kubernetes, there's control planes, this, that, it's hard to know exactly where your resources are being allocated, where the spend is going. And that is very important to the longevity of any project that you're working on. So they're gonna talk about something they built called Infraspend, which is a data set and dashboards to analyze where your spend's going and talk about how to think through these things for resource-intensive ML workloads. So with that, Richard and Konstantin, please take it away.
Thank you. Cool. So our topic is called Measuring and Optimizing Kubernetes Usage at Lyft.
Hey, I'm Richard. I work at Google, and I'm not a picture person, so there's a picture of my cat instead. You can see that she's learning machine learning, so.
That's good. So I am Konstantin. I sort of put a few logos to make myself seem more legit. So I recently graduated from Northeastern kind of last year. And before that, I interned at Instagram and Stripe working on product and machine learning. And then at Lyft, I joined a team called Capacity. And basically, the point of the Capacity team was that our infrastructure costs were increasing a lot, and we needed to build visibility and tooling to control that. So I want to give you guys a brief overview of what you're going to learn. Basically, we're going to try to cover a lot of ground, and I want you to understand sort of like our journey with cloud infrastructure spending at Lyft. A little bit about sort of the way that we use Kubeflow, some of the machine learning workloads, how those complicate our cloud infra spending story, and then finally how we built a product called Infraspend, and how we extended it to track platforms like Kubernetes and also other multi-tenant platforms. And I kind of want you guys to keep in mind why this is important, why it matters, and then hopefully maybe if you don't have something similar, your organization can inspire you to try to take on this journey. Cool. So like I said, around the time that I joined, our infrastructure bill was increasing quite a bit. So at Lyft, our philosophy with infra is that we want to give teams autonomy to spin up whatever resources they need. But this was a problem because it also meant that we pretty much had no idea where like our spend was going until we built a spreadsheet. So my manager, who I guess at the time was not a manager, started this initiative at Lyft, and he was just scraping AWS APIs and uploading that data into Google Sheets. And then around the time that I joined, we started working on something called Infraspend 2.0, which used much more sophisticated technologies to pull this thing called the cost and usage report from AWS and process it using sort of like standard infrastructure, like Lyft's data platform, and create this like nice data set that we could build on top of So don't want to dive into it too much right now, but there are two features that we should keep in mind. One of them is that we wanted to derive something called a Lyft label, which lets us track spending and resources in a way that's like unique and identifiable across Lyft and specific to different platforms. And the other important feature is that we introduce this notion of true cost. And so basically in like the old sort of like world and even in the cost and usage report in AWS, you have different identical usage within the same time frame that has different values. So you can have two identical nodes that you're getting billed for, and you can be paying $2 for one and $1 for another, even though they're being used at the same time. So this is kind of important later on as we talk about multi-tenant platform attribution and sort of like fairly billing different teams. We'll go through these real quick. So this is kind of like one of the entry points to Infraspend. It lets you choose different dashboards. So there's like the deep dive dashboard, executive dashboard, stuff like that. And this is a view that people tend to like a lot. So you can see that the time series with like the stacked bar chart. So that kind of shows like each of those is like a cluster or like a data store. And then if you can read up there, this is just like the series that we see for the mapping organization at Lyft over the course of a week. And so providing this kind of like rich data really helps get people to like look into it and like dig into it because it's so easy to digest. Another Infraspend demo, trends, executive dashboards. So I guess the complication here is that in the olden days when you had a single resource like an auto-scaling group or like a cluster, you would have like one service running on it. So you might have like the pricing service, which runs on the pricing cluster. But obviously with multi-tenant platforms, that's no longer the case. So you have like one Kubernetes cluster and you're running hundreds of services. And so being able to see the cost of the Kubernetes cluster is not that useful. So for example, this is like the number of EC2 C5 18x large instances that we were running in our core Kubernetes clusters at one point. And then this is further complicated by the fact that we've had dozens of different clusters at Lyft that we needed to attribute. So there's the core Kubernetes clusters in flight and machine learning clusters. So Richard is going to speak a bit about Kubeflow and some of the features that we've used.
Okay, thank you. So as Konstantin mentioned, at Lyft, they have this platform that's called Lyft Learn for a machine learning platform. And it uses components from Kubeflow. So that's what I work on at Google. So one of the problems that Konstantin mentioned is like Kubernetes reduces visibility into your usage, right? And this is like exacerbated by the fact that the machine learning workloads are quite complex. So we're going to take a tour of Kubeflow, and we're going to look at how different machine learning workloads is going to affect spending and usage. Okay? So notebook instances, right? So this is pretty straightforward. So you, as a user, you can build all your notebook dependencies, like your Python libraries, your TensorFlow libraries, and into this one container. You start a container instance, and you can open up the web portal, and you use you can type your training code there and run everything in a notebook, right? So what's a usage pattern like? You're most likely using it as individual users, right? So anybody, any data scientist or any machine learning engineer can just spin up a notebook, okay? And you want that to be a high availability, right? If you want to start a notebook session, you want it to start right away. You don't want to wait 30 minutes or so for it to start up. So most likely you have multiple users using multiple notebook instances, and the usage pattern kind of grows like a linear fashion. And but you could have problems like potentially idle notebooks, right? Someone starts a notebook session, use it for a couple hours, and just like forget about it, and you have these idle resources sitting around, okay? So that's for notebook instances. Another possibility is like KF serving, which is there was a talk earlier on this, but basically this is the scalable Kubernetes native inferencing service. For this, you want the usage to be, most likely is also high availability, but you also want the ability to quickly add capacity, right? Let's say your call volume for the inferencing calls, right? You have a certain spike. This requires you to quickly adjust to the additional level of demand, right? And potentially you need a lot more GPUs. So you can see that this is quite different from the notebook instance where it grows fairly linearly. And for notebooks, your usage is most likely attributed to individual users, but in this case, it's more likely to be attributed to a service or a team. Okay. We also have Kubeflow Pipelines. So this is a component that allows you to build end-to-end machine learning workflows. So we can see an example on the right-hand side. The writing is a little small, but you can see it says like creating a cluster. There's a transform, train, predict. So it takes these machine learning steps and builds the dependencies into this dependency graph. And you can run these workflows regularly on the schedule, right? So what's that like in the real production environment? Well, you could have, suppose you have some resource constraints on some of these steps, right? And you have multiple of these pipelines running in parallel or running together, right? So you could have these bottlenecks because some steps like the training steps may be very resource intensive. And so you could have several of these pipelines competing for the same resources. Okay. And this is my favorite, hyperparameter optimization, because this is the component that I work on the most. So a little bit about hyperparameter optimization. Right? So hyperparameters are the parameters that are external to the model. Unlike the model parameters, which is something in the training process, you learn the values of the model parameters, right? For hyperparameter, you set the values of these parameters before you start the training process. So examples are like the learning rate, number of layers, batch size, kernel type, and so on. Okay? So the process of hyperparameter optimization is finding the best values such that the model performance is maximized. So in Kubeflow, there's a component called KTIP. That's basically the open source implementation of hyperparameter tuning on Kubernetes. And what it does is you just initialize your search space and your model. And there are two main constraints for a tuning experiment. Right? There's objective value, which is, let's say you're trying to optimize your prediction accuracy, right? So you can set a goal, like I want my prediction accuracy to be 90% or something. There is also a budget. So this is like how many trials I want to run. Right? So these are the constraints for my experiment. And in each iteration, what it does is it gets the next set of parameter suggestions from a suggestion service through this call called get suggestions. And that gives you the next set of your hyperparameters to use. And then this gets plugged into a trial. A trial is just a running instance of your whatever it is you're trying to optimize, your experiment. Right? So it runs a trial using the parameter values, and it produces some metrics values. And these metrics get reported back to the reporting service, and it continues, right? So how does this affect our spending story? So a tuning job can be very CPU intensive, right? Because you could have potentially many of these. I should actually explain. Each trial is actually a training job, right? Because you're launching a job and you're training for like some number of epochs, and then it produces some set of metrics, and giving you these metrics, we determine if this is a good set of hyperparameters or not, right? So if you're using really bad values, okay, we can terminate the experiment early. But sometimes if you're trying to optimize for like the additional 1% or 2%, if you're using like, for example, Bayesian optimization, right? That means we want to explore a certain range of values more. So we're basically running iterative training trials on the same range, set of parameters. So that could be very resource intensive, right? And that can have a lot of high capacity demand. And depending on how much resources you have available, you can also configure how many trials you want to run in parallel. So what does it all mean? So we've seen a few examples, like we've seen distributed training, hyperparameter tuning, serving, and notebook instances, right? So all of these have very different usage patterns, right? Some of them are very high volume, high demand. Some of them require very high availability, and some are very resource intensive, right? So, and this is further complicated by the fact that your cluster could be multi-tenant, right? You could have several different teams, and each team could be doing different things. Some might be more doing more training, some might be more experimenting with notebooks, right? So because we mentioned earlier, the Kubernetes hides away a lot of these details. So if everything is just aggregated at the cluster level, it's very difficult to attribute what your actual spending is, right? So multi-tenancy is a problem that Kubeflow itself is trying to address. And in our upcoming 1.0 release, we want to have a complete story for multi-tenancy. But we are more working towards like the user isolation, right? So being able to create a profile where each user can have like an isolated set of resources to use. So another part of the story is how do we attribute usage in the multi-tenancy world? So, and that's what Konstantin is going to tell us about.
Cool, thanks. So in the first part of the presentation, I talked about Infraspend without multi-tenant platform attribution, where you kind of see resources in aggregate. And so now I'm going to talk about some of the infrastructure that we built to allow subdivision of those shared resources, such as our ML platform and our KTIB workloads, and the way that we thought about it at Lyft. So essentially, we wanted to build a system that is modular and extensible. So we wanted to start with Kubernetes, but we wanted the concepts that we use for multi-tenancy to extend to other platforms like ETL, experimentation, and so on and so forth. And finally, we wanted to make this a platform for platforms. So we basically wanted to provide a clear way that platform owners can provide their attribution data to us and subdivide their resources, because partially our philosophy is that platform owners understand how they should attribute their resources best. So there are basically two important concepts to talk about. The first is like the definition of a platform. And so the way we think of it is a platform ties together a bunch of resources. So in the AWS world, you might have databases and S3 buckets and EC2 clusters as different resources. And we want to unify those under a single platform tag, and then provide an attribution schedule, which tells us how we should break down the cost of each of those resources to different attribution labels. And so that ties into the label concept that I brought up in our Infraspend 2.0 dataset. So quick aside on the properties of an attribution schedule. Basically, for a certain attribution schedule, all the platforms that we specify should be in there have to be defined. And then within each of those platforms, there must be data for every single hour. And then the usage has to add up to exactly 1. So this is essentially, it's a Hive table that breaks down the hourly cost of a certain platform according to different attribution labels as a %. And in terms of how attribution schedules can be generated, we essentially support 3 different methods for attribution schedule generation. The first that I'm going to talk more in depth about in this presentation is like a custom pipeline that we built using Prometheus to pull Kubernetes metrics. And currently we support CPU and memory in that. And so Kubernetes cluster owners can choose whether to have their platforms attributed based on CPU or memory. If that doesn't work for platform owners, there are sort of 2 other options that I'm just going to touch on right here, but not necessarily go into like the details of. So basically, either platform owners can stream their usage to us through like Lyft's standard analytics infrastructure, or they can support their own attribution schedule that has the properties that I brought up earlier, and we can consume that as well. So they sort of go from least involvement for the platform owner to most involvement for the platform owner. Maybe a quick aside, so in terms of how this works on the back end is we keep a bunch of different attribution schedules. Some of them might be reported by platforms. Some are the Kubernetes pipelines on top, and we unify those into a single step that we stage to join into our Infraspend data. So I guess without further ado, I'll talk a little bit about how we provided namespace level attribution to our Kubernetes workloads first. So here's a practical example of how this works. Up top, you see the cost of different resources in our raw Infraspend data. So you have, for example, at 1 p.m., cluster 0 costs $1. And on the attribution schedule, down below on the left side, you can see that the usage of the cluster 0 platform should be subdivided, like 50% of it should go to the free namespace, 30% goes to our first service, and 20% goes to our second service. And then after the join step, you can see that usage is subdivided in the enriched Infraspend data. Another thing that we had a lot of discussion around and are actively working on to build more support on are different cost models for platforms. So in the case of Kubernetes, we've like entertained a bunch of options. So we started off by building the CPU allocation cost model, and I guess some of the other ones are fairly intuitive in terms of what they might look like under the hood. But essentially, what this means is like we look at the total number of CPU cores that are available on a cluster within a certain instance type in aggregate, and then we divide the number of cores requested by any given namespace by the total number of cores on the cluster within that instance type. Another aside here is that we think of Infraspend as being about allocation rather than utilization or efficiency. So I guess like in the non-Kubernetes world, this means that like if your team spins up a node, even if they don't use it at all, it goes to your team. And similarly with Kubernetes, if you request some resources, even if you're not using them effectively, they should be attributed to your team. However, we are actively working on like developing different features and like different products, or potentially even integrating the two to support more visibility into the efficiency of different allocations. I guess one other bit is, although we don't really think of Infraspend as being about efficiency, we kind of have a feature that allows us to monitor the efficiency of our Kubernetes platforms, which is our unallocated capacity. So according to our cost model with like the CPU allocation things that I discussed, we have a balance, which is the leftover cores after you've accounted for all the namespaces that have requested CPU cores in the cluster. And so we surface our unallocated CPU capacity in our data. In terms of how we collected our Kubernetes metrics, we spun up a very lightweight microservice, which scrapes metrics for each of our Kubernetes clusters. So Kubernetes cluster owners can register their cluster, which essentially means that our service will scrape that cluster's Prometheus, and it issues a couple of different requests. So one is that we take kubestate metrics from Prometheus for CPU core requests, for running pods, as well as the CPU capacity, memory capacity, and more recently, pod labels. So I'll go into a little bit of detail about how we use pod labels, but essentially it's to do custom tag attribution on things other than namespaces for annotations that users might add to their pods. So downstream, our service emits our Kubernetes usage data, so like the requests and capacity and so on, into our Hive infrastructure. And there are like 2 steps, essentially. And I kind of, for illustrative purposes, put screenshots of what that code looks like, but compressed it so you can't really read it. Hopefully that's kind of entertaining. So on the left side, we essentially do this computation that I discussed, where we group all our requests by namespace, and then we divide those by the total cluster capacity and by instance type as well. So I did that in kind of HiveQL. I definitely would not recommend that. And then the step afterwards is we run interpolation. So because we have a bunch of different instance types and a bunch of different Kubernetes clusters, we want to make sure that even if one of our dependencies, like kubestate metrics or Prometheus, is offline, that doesn't get surfaced in our data. So we kind of just want to be notified of it, but not necessarily have it break or create gaps in our data. And so we run interpolation, where if we're missing data for a certain hour, then we'll fill it in with the previous hour. So sort of to the point I just brought up, because there are lots of different Kubernetes clusters, and within those clusters there's lots of different dimensions that we want to support, the operational load has actually been, or at the beginning of the project was actually fairly high. And so some of the more challenging things were just getting the right visibility in our service to scrape those metrics, so that we're notified essentially as soon as possible if one of the dependencies like kubestate metrics or Prometheus is offline, and also to notify the teams that actually own those clusters that they should make sure that their systems are functioning properly. And then the other is actually that similarly with like rollups and different dimensions being present on the data, like the distinction between node and instance type in or node and instance in like kubestate metrics, basically it was really important to test assumptions about our data at every single step. So it kind of seems like a fairly simple pipeline, but in reality there's probably like 7 or 8 sequential components, and we've kind of experienced like different unexpected behaviors at most of them. So it's really important to do sanity checks at every step. Cool, so that's a little bit of details on how we implemented this under the hood. I guess up next I wanted to just go through a few screenshots and like talk through what the product experience was with Infraspend 2.0 with Kubernetes. So this is another screenshot from our product. So one of the things you can see on the left side in like the green is our either daily or hourly usage on just like bare instances. And on the right side, you can see our hourly usage on Kubernetes. So the thing that I want to highlight is that like almost categorically, all of our Kubernetes deployments were over-provisioned when we first went on the platform. But over time, partially because we've had this data and it's like in like everyone's face, we've been able to like tune the sizes of different workloads and for almost all of them make them, or for all of them really, make them more efficient on Kubernetes from a cost perspective. So this is another sort of a couple screenshots from a presentation about how Kubernetes saves money. And same story, like on the left side you have the like the raw EC2 usage, and then on the right side you have the Kubernetes usage after it's been tuned. So the big impact there was that it lets us track our raw infra and Kubernetes usage side by side, and also kind of to that point, it lets teams throughout the company see all of their cloud products in one place. The other thing that I brought up is this like unallocated cluster capacity that we tracked. And so you can see that as we started migrating to Kubernetes, our unallocated space on our clusters was continuously increasing. And so it became kind of a significant cost that Infraspend was able to surface. And because we had this, it got a lot of people to look into it and try different things around tuning autoscaler policies, and also deploying new services. So raise awareness of inefficiencies from an allocation standpoint. And so there have been a few things that we've done to make our Kubernetes deployments more efficient. I think the biggest impact was tuning cluster scaling policies. So like removing nodes when their CPU utilization is higher than previously, and also for tuning pod scaling policies. So quick aside, yeah, so a lot of the stuff going forward is kind of like additional features that we've been adding to our Kubernetes for Infraspend infrastructure. So we're working on supporting more allocation schedules and adding different dimensions. So we've had a few teams experiment with like looking at their attribution data based on a container or based on custom pod labels that they emit through our usage tracking service, and also working with teams to build custom views into the data. So as an example of one of these custom views, this is an Infraspend dashboard that our machine learning platform team built, and it basically just breaks down the costs of just their Kubernetes clusters and lets them look at like namespace level attribution and have different sort of like visualizations and charts and trends. And then with regard to different dimensions, this is another chart that we have that further subdivides the namespace level attribution to containers and then filters out just the containers that correspond to Spark jobs. And so this has been kind of useful as well because now you can see who's using Spark specifically on Lyft Learn through the same data set. And this sort of goes with the point about being able to build custom dashboards on top of the data set that we built. So I guess almost everything that we use is open source, and it should generalize to like different vendors. I think we have some stuff in flight potentially to integrate things like Wavefront and so on. But the technologies that we use are essentially Prometheus and Kubernetes and kube state metrics. Ingest that data into Hive. We make it usable through Druid. So Druid allows us to like query the data much more quickly, and we display it through another Lyft open source project called Superset, which is essentially how we've built all the dashboards that I've shown screenshots of throughout the presentation. Cool. So yeah, I mean, going forward, we want to onboard more platforms to Infraspend, provide finer granularity, talk about efficiency more, stuff like that. Cool. Thanks.
All right, questions?
So prior to using Infraspend, you mentioned that Kubernetes kind of clouded your visibility into cost compared to the cost and usage data that AWS provides. But now that you have Infraspend, would you say that you have more visibility into your costs than you did with AWS cost and usage reports?
That's a good question. I think, so in general, we kind of have more granular visibility with Infraspend in some sense because we see our usage disaggregated across different clusters. So if we have one service that's running across like 4 or 5 clusters, we see our usage across those 5. There are some, I guess, like challenges around the unallocated portion of our Kubernetes clusters. So that that might make it a little bit harder, but yeah. Yes.
Question. You mentioned that you have different type of allocation based on the different team. So one question I was wondering is, if you have different teams that are, like, let's say I've got a workload that is CPU driven while another one that is memory driven, and they both share within the same cluster, how do you split them apart?
So when we were first building the multi-tenant platform attribution with Kubernetes, GPU wasn't really supported through kubestate metrics. Not sure if that's still the case, but we basically could collect attribution schedules for either CPU data or for memory data. And so we did some like ad hoc analysis for our platforms to find whether CPU or memory made more sense in terms of like how that allocation would come out. And so for our core platforms, we found that it was CPU. For other platforms, like for some of our ML workloads, we found that it was memory. And so we're basically allowing platforms to choose which of those standard Kubernetes models they can attribute their platform based on. And if neither of those really works for them, then they can either report their own usage or support their own allocation schedule.
So is it fair to say that if you basically have got different use cases and instantiating into different platforms, like one platform for that type of workload, another instance of platform for the other?
So you said, so if there's 2 types of workloads, then you have to instantiate 2 types of platforms.
That's so not necessarily, but like practically speaking, for example, in our core clusters, we find that like 95% of those workloads are CPU bound, and so we feel somewhat comfortable attributing those based on CPU.
Okay, so I would like to know that in Lyft you have a version of Kubeflow called Lyftflow, and it's modified from the Kubeflow open source project, right? And I would like to know the difference between the Lyftflow and the open source version Kubeflow. Yeah.
Richard, do you know?
You're talking about the Lyft Learner, right?
Oh yeah, Lyft Learner. Okay. Yeah.
So Lyft Learn, as far as I know, is a collection of, it's like an internal machine learning platform at Lyft. And my understanding is they use components from a released version of Kubeflow. So they may have, like for an example of the hyperparameter tuning, I think they built around a UI to simplify some of the like getting started experience. Because if you use the Cative just out of the box, you have to configure the CRDs and all that stuff, right? So they have a pretty nice user interface, and it's more specific towards Lyft, but it's not a different version of Kubeflow.
Okay, so and in the future, is it possible to open source those different features? Maybe because in the Lyft they have a good feature, and that is that Kubeflow doesn't have, and maybe Lyft can contribute to Kubeflow. Maybe, I mean, yeah.
I think they should.
Agreed.
Okay, that's it.
Cool. Thank you, everybody. Feel free to continue the conversation in the hallway. Yay!
Thanks.